Filling materials: temporary, permanent, materials for therapeutic and isolating liners, positive and negative properties, indications and contraindications for use, method of preparations and application of filling materials. A lecture for second-year students of the third semester of dental faculty. Classification of. Depending on the material of manufacture, filling materials are divided into metals, which are amalgams, alloys, and pure metals like gold, and non-metals, cements, plastics, and composite material. Depending on the purpose, there are filling materials for temporary fillings or dressings, permanent fillings, treatment liners, materials for intermediate restorations, bases and liners, and materials for root canal obturation. Classification of temporary filling materials: zinc sulfate cements or artificial dentin paste, zinc eugenol cements, polycarboxylate cements, zinc phosphate cements, glass ionomeric cements, and polymeric materials. Temporary fillings are intended for short-term isolation from 1 day to 2 or 3 weeks, sometimes for a longer time, of the formed and treated caries cavity in order to preserve the medication left on the cavity bottom, at the orifice of the root canal or in canals of the teeth directly, including to monitor the results of treatment of root canals of teeth. In addition, temporary fillings are applied in the case of a delayed treatment for a longer time, up to 3 months. Treatment liners. Materials recommended for usage as treatment liners are materials based on calcium hydroxide, which are the most universal means of application as treatment liners. They provide an odontotropic effect, prevent the penetration of microorganisms into the pulp of the tooth. However, the material has low mechanical strength and dissolves in the oral fluid. Zinc eugenol cements, used as therapeutic liner or temporary filling. Eugenol is an antiseptic of plant origin. When mixing zinc oxide and eugenol, cement is formed, while the curing is based on the chemical reaction on the formation of zinc engenolate. And combine medical pastes, which have a wide range and include for the intended purpose odontotropic agents, antiseptic materials, proteolytic enzymes, and other materials. Combined pastes, as a rule, do not harden and are used as a temporary material with subsequent placement. Here you can see some examples of the treatment liners. Materials for intermediate restoration. An intermediate restorative material is a gasket located between the filling and the dentin of the cavity. These materials are divided into bases and liners. The base can withstand chewing pressure and the load associated with the condensation of materials. The optimal thickness is 0.75 to 1 mm. Liner is prepared for cements, protects the pulp from the chemical effects of a constant reducing material, but does not protect the pulp from thermal stimuli. Classification of isolating liners: zinc phosphate cements, polycarboxylate cements, and glass ionomer cements. By composition and curing mechanisms, there are classical two-component glass ionomer cements, hybrid glass ionomer cements of double or triple curing, one-component light curing glass ionomer cements, and isolating varnishes. Zinc phosphate cements. Their composition are two components, powder and liquid. The powder consists of 75 to 90% of zinc oxide with the addition of magnesium oxide 10%, silicon dioxide, calcium oxide, aluminium oxide, and a small amount of pigment. On the slide you can see representatives of the zinc phosphate cements. Polycarboxylate cements. There are also two components, powder and liquid. The powder in its composition contains mainly zinc oxide, 1 to 5% of magnesium oxide and calcium oxide. Some materials contain up to 40% aluminum oxide and the highest amount of tin fluoride or other fluorides. A liquid is 40 to 50% aqueous solution of polyacrylic acid or an acrylic acid copolymer. Glass ionomer cements. There are two components, powder and liquid. The powder contains finely dispersed aluminofluorosilicate glass, consisting of finely ground glass, calcium fluorosilicate, and aluminium with a particle size of 25 to 40 micrometers. Thus, the main components of the powder are silicon oxide, aluminum oxide, calcium oxide, with the addition of a small amount of sodium fluoride, aluminum fluoride, and potassium fluoride. The liquid is a 50% aqueous solution of polycarboxylic acid copolymer with the addition of 5% tartaric acid. In some materials, a copolymer dried in a vacuum is added directly to the powder. Then only a powder is in the kit, which is kneaded in distilled water and called aqueous cement. Depending on the composition and mechanism of hardening, all glass ionomeric cements are divided into classic, which have two components, hybrid, which have double or triple curing, and one component cement. Cavity varnishes. Cavity varnishes are one of the varieties of liners. They are designed to protect the pulp from the toxic effects of film materials. Their ingredients are filler, zinc oxide, solvent, acetone or chloroform, natural or synthetic resins, classification of permanent film materials. Cements. Mineral cements, which are based on phosphoric acid, are zinc phosphate, silicate, and silicon phosphate. Polymer cements, which are based on polyacrylic or other organic acid, are polycarboxylate and glass ionomer. Polymer film materials, plastics, unfilled based on acrylic resins or based on epoxy resins, and filled materials, composites. Compomers, ionomeric with resins. Armacers, organically modified ceramics. Metal film materials, amalgams, silver or copper. Mineral cements are one of the oldest groups of permanent film materials. There are zinc phosphate cements, silicate cements, and silicon phosphate cements. The zinc phosphate cement powder consists of zinc oxide, magnesium oxide, silicon oxide, and fractions of aluminum oxide. Silicate cements consist of silicon oxide, aluminum oxide, calcium oxide, fluoride compounds, and compounds of iron, cadmium, manganese, and nickel in order to give the material the necessary shade. And silicon phosphate cements is a mixture of silicate cements and zinc phosphate cements. Zinc phosphate cements are presented on this slide. On this slide, you can see silicophosphate cements and silicate cements and their representatives. Polymer cements. The desire to improve the characteristics of mineral cements has led to creation of a new generation of materials, polymer cements, which include two groups: polycarboxylate cements and glassionomer cements. Composition of polymer cements. The polycarboxylate cements consist of zinc oxide with an addition of magnesium oxide. The liquid is a 37% solution of polyacrylic acids. Sometimes distilled water is used as a liquid, and cements with such the equipment is called aqua cements. Glassionomeric cements. A classic glassionomeric cement is a powder liquid system. The powder once again consists of calcium aluminum silicate glass with the addition of fluoride. In order to give the cement radial opaqueness, compounds of barium, strontium, and lanthanum can be added to the composition of the powder. Polymer filling materials. These are the materials during the curing of which the polymerization process takes place. The reaction of combining a large number of small molecules, monomers, into a large one, the polymer. Polymeric materials are divided into unfilled and filled. Unfilled materials were developed in 1939 and are fast-hardening plastics of cold polymerization based on acrylic or epoxy resins. The filled materials were developed in 1964 with the discovery of bis-GMA resin, and these chemical curing materials are based on them. Unfilled polymeric materials are divided into two groups: acrylic resin and epoxy-based. They are presented as a powder liquid system. The powder are polymer particles, polymethyl methacrylate, pigments deposited on the surface of the polymer, initiator. A liquid is consisting of monomer, methyl ester or methacrylic acid, inhibitor, hydrocoine, spontaneous polymerization of the monomer. The epoxy-based polymeric materials are paste-paste system. The resin contains low molecular weight liquid epoxy component with elements of porcelain flour and quartz, and the hardener contains a catalyst that promotes the transition of epoxy resin into a solid state. The main structural elements of composite materials are polymer matrix, anorganic filler, and silane. On this slide, you can chemically see the structure of composite material. The polymer matrix of composite material consists of monomer with a high molecular weight, bis-GMA or its derivatives, UDMA, etc., and a monomer, diluent TEG-DMA. The polymer matrix ensures the fluidity or plasticity of composite in its original state and the stability of form, monolithic, and tightness after polymerization. On this slide, molecules of these monomers are demonstrated. The polymer matrix. The matrix also includes a photoinitiator or polymerization to start polymerization, a polymerization catalyst to activate polymerization, a polymerization incubator to increase the operating time and extend the shelf life, an absorber of ultraviolet light to reduce the change in the color of the material when the ultraviolet light hits it. The main problem of composites is shrinkage during polymerization. On average, it's about 1.8 to 3.5%, and this is due solely to the polymer matrix. Shrinkage of the composite leads to polymerization stress at the composite and tooth boundary, separation of material, micro leakage, staining, micro cracks of enamel, postoperative sensitivity, and secondary caries. Inorganic filler, more than 50%, is consisting of silicon oxide, barium, strontium, and zirconium glasses, aluminum oxide, hydroxyapatite, etc. The filler determines the strength and abrasive stability of the composite and reduces the total shrinkage up to 0.5-0.7% of the composite, improves the aesthetic properties of the material depending on its particle size. Interfacial silane layer, which may be called aprits or surfactants, provides a connection between the filler and the polymer matrix. The surface of the filler is treated with silane, due to which a chemical bond with organic matrix is formed. The filler particles become water repellent. The color stability of the material improves by reducing water absorption, strength, and wear resistance increases. Classification of composites by polymer matrix composition. First is pure metacrylates, traditional composites. Second is acid-modified metacrylates, compomers. Third is inorganic organic matrix, armachers. And fourth is epoxides with open rings, siluranes. Compomers. They appeared in 1993. The material direct by Dentsply, combined with properties of a composite material and a glass ionomer with a modified matrix and filler. Features are: first, an organic filler contains silicon compounds used in the manufacture of glass ionomer cement. Second, in the composition of the matrix, in addition to traditional monomers, acid-modified groups are introduced, which provides photopolymerization, as in a composite, then an acid-base reaction as in glass ionomer cement. In terms of aesthetics, compomers are superior to glass ionomer cements, but inferior to composites. They have high water absorption and hygroscopic expansion of the material. On this slide, you can see the representatives of compomers, the direct by Dentsply and Compoglass by Vivadent. Armachers appeared in early 90s, and the name stands for organically modified ceramics. Their features are inorganic filler, 70 to 80% of mass is barium glass and modified fluorapatite. In the composition of the matrix, in addition to traditional monomers, polysiloxane molecules, the main structural element of ceramics, are introduced. Advantages are low shrinkage due to less reduction of polysiloxane chains during polymerization. In terms of physical and mechanical properties, they are identical to microhybrid composites. The representatives of armachers are Admira by Voco and Definite by De Giusse. Silurans, a new type of material from two components: siloxanes with high hydrophobicity and biocompatibility, and oxyrans with low shrinkage and high stability due to the effects of various factors. Their features are good biocompatibility, low water absorption, and resistance to light, which means they have long working time. Oxyrans were introduced into the matrix. thereby reducing shrinkage to 1%, while the amount of filler remained high at 80%. The representatives of silarans are Filtech silaran by 3M SP. Classification of composites by consistency or density. Medium density, low density, and high density. Classification of composites by polymerization type. First is chemical curing, second is light curing, and third is mixed double curing, which means that both chemical curing and light curing can be used to cure these composites. Classification of composites by purpose. For the restoration of frontal teeth, for the restoration of lateral teeth, and universal composites. Classification of composites by filler particle size. Here you can see different sizes of particles. From left to right, it's 1000 nanometers, 600 nanometers, 400 nanometers, 75 nanometers, and 20 nanometers. Classification of composites by filler particle size. First and the oldest are microfilled composites, which consist of particles of 1 to 50 micrometers. Then microfilled composites, 0.04 to 0.2 micrometers. Hybrid universal have particles of about 1 to 10 micrometers. They have different types of hybrid composites, with a conventional filler, with a thin filler, with an ultra-thin filler, and with a submicron filler. And the latest invention in composites are nanocomposites, which have particles of size of nanometer, and nanofilled composites have particles of size 1 to 100 nanometers. Nanohybrid composites have particles like 1 to 100 nanometers and a hybrid layer. And super nanofilled composites, we have a particle size of less than 50 nanometers. Microfilled composites. They have a filler of 60 to 70% of mass with large particles like quartz, ground glass, or ceramics. The advantages of microfilled composites are the high strength, but they have a lot of disadvantages, such as roughness of the surface, inability to polish them to dry shine, which leads to adhesion of plaque, and instability of color, as well as a rapid abrasive wear of the polymer matrix. Filler particles fall out of it, leaving voids, and the surface quickly becomes rough. The representatives are Evicrol by Spofa Concise by 3M SP, Adaptic by Dentsply. Nowadays, these composites are obsolete and are not used anymore in practice. Microfilled composites have a silicon dioxide filler with a very small particle size of 0.04 micrometers, which gives perfect polishing ability due to a dry shine of the material. And here on the pictures you can see a homogeneous microfilled composite on the left and non-homogeneous microfilled composite on the right. In homogeneous microfilled composite you can see even spreading of filler particles, and in non-homogeneous microfilled composite, these filler particles are assembled in some globes. Microfield composites have very good polishability, glossy resistance, and elasticity, but they are low on fillness. The filling is 20% of mass in homogeneous composites and 55% in non-homogeneous composites, very low resistance to mechanical stress, high shrinkage during polymerization, water absorption, and high coefficient of thermal expansion. They are not contrast on X-ray, which makes us think that there is no filling on the X-ray, but actually this filling may be done from the microfield composite. The representatives are Prodigy by Kerr, Heliomolar by Avoclad Vivodent, and Durafil by Kuzer. The hybrid composites. They have a mixture of particles of different sizes from 1 to 10 micrometers, which combines the physical and mechanical characteristics of macroparticles and microfillers. The fullness of particles is 73 to 82% by weight and 55 to 65% by volume. With these materials, the real practice of adhesive restoration begins. On the picture, you can see structure of hybrid composite, and you can see that there are particles of different sizes in this composite. They have a lot of good points, like sufficient strength, acceptable aesthetics, and radio opaqueness, but they are not ideal, and the surface and polishing ability is worse than of microfield composites, and they have an unstable dry shine. The representatives are Prismophil, Tetric, and Petrak hybrid. Nowadays, they are not actively used, but only in budget clinics. Microhybrid composites. A mixture of particles ranging from size from small to ultrafine, 0.04, 0.5, 1, and 3.5 micrometers. The average particle size of the filler is 1 micrometer and a modified polymer matrix. On the picture you can see a microhybrid composite. Microhybrid composites have a lot of quality points, like the strength, resistance to breaking, low water absorption, coefficient of thermal expansion is close to the hard tissues of the tooth, good polishing ability and color stability, radio opaqueness, wide scale of shades. But they have high polymerization shrinkage due to the amount of matrix in the composite and small size of particles. On this slide, you can see a table of manufacturers and names of the microhybrid composites, which you can find in the market even now. On this slide, you can see different types of microhybrid composites. So what should be the properties of the material for dentin restoration? The material for dentin restoration should have high elasticity. To compete with the natural elasticity of the dentin, it should have fluorescence, low shrinkage, optimal opacity with high saturation, orange red shade, camouflage effect, compression resistance, and ability to conduct light. Preheating of the composite material to 56 to 60 degrees Celsius improves the plasticity of the material, which means that a portion of the material is better glued and modeled, improves the degree of conversion, which means the depth of polymerization is much bigger, which leads to an increase in the modulus of elasticity and strength, and the level of polymerization shrinkage and polymerization time decreases, which can help us with the restoration of dentin. On this slide, you can see different types of composite heaters used for preheating composite material. So, microhybrid composites for dentin restoration are well withstand increased stress by their elasticity, have good gluing, and good light reflection and opacity, which are all positive properties for dentin restoration. But they have some undesirable properties for animal restoration, which are the rapid loss of shine, which requires the polishing after 1 or 2 years, increased abrasion of 7 micrometers or more per year. A natural animal, it is 1.2 micrometers per year, which is almost 7 times more than in natural animal. Nanocomposites. As a filler in organic particles the size of atoms, 1 to 100 nanometers are used. Due to chemical modification of the filler, its particles do not stick together, which can significantly increase the fullness of the composite to 82 or 84%, and consequently reduce polymerization shrinkage to 1.5 to 2%. Part of the filler nanoparticles is assembled into clusters, large particles from 0.6 to 1.4 micrometers, which provides a combination of the aesthetics of microfield and high strength of hybrid materials. On this slide, you can see the names and manufacturing companies which make nanofield and nanohybrid composites. The properties of the optimal composite from animal are high opalescence, same refractive index of light with animal, high transparency, variable brightness, and the ability to increase brightness when increasing thickness, rigidity after polymerization, good polishing ability, and translucency. On this slide, you can see the phenomenon of opalescence. As you can see, the edge of the teeth, the central incisors in this picture, is more transparent than the rest of the tooth, which reflects that animal has more transparency and the dentin has more of opalescence and is not conducting light as well as animal, which is also used by us during the restoration of teeth. What are the properties of nanohybrid composite for animal restoration? The positive properties are surface gloss and abrasion resistance. And undesirable properties are poor gluing, light scattering, which means that our material will appear gray, and low elasticity, which is why these composites are not used for cervical defects. It is advisable to apply nanohybrid composites in small portions by lateral fragmentation within the polymerization thickness. On this slide, you can see a nanocomposite Estet X HD. There are also some combined materials which combine the qualities of nanohybrid composites and microhybrid composites. And you can see the composite Essentia by GC company. Bulk fill materials are used for filling volumetric defects using a simplified technology. These materials are recommended to be applied in large portion of 3 to 5 mm with simultaneous illumination by polymerization lamp. They are positioned as materials with reduced stress and shrinkage and can fill the entire cavity with just one portion of material. You can see the names of these materials on the slide. Build-up composites or composite cements of double curing for fixing fiberglass points and forming a tooth core are also used for restoration. They are incompatible with adhesive systems of the 5th generation and work with only 4th, 6th, and 8th generation adhesives. The names of these composite materials are on the left, and these composite materials are stored in double syringes, which contain the base and the catalyzation paste, and they are mixed together in the special needle, which helps us with distributing the material into the tooth. On this slide, you can see additional composite modeling accessories like brushes and modeling resin. The microbrush, which we may use for inserting adhesive into the cavity, can also be used to model the composite material because it does not stick to the composite, has a soft working part, and is useful for modeling a portion of material and creating some texture on the top of material. On this slide, you can see the sequence of use of composite modeling tools. What are the rules to work with the composite to avoid the formation of air pores in restoration? First of all, the portion of composite is squeezed out of a syringe and cut off with an ironer, and pulling and picking on the material is unacceptable. The material is not rolled into balls in the fingers. You can use an ironer in a pellet to destroy the dispersion phase of a portion of material to improve its thixotropy. The portion should not be more than 2 mm thick. Only case when the thickness of the layer may be more than 2 mm if you use the backfill material. A portion of the material is carefully rubbed into the hard tissues of the tooth, first adapting to the surface and only then proceed to model the shape. Smoothen the surface of the material with brushes with a small amount of resin. Resin is also used to attenuate the adhesion of the material to the tool. And strictly observe the working time of the material while modeling to ensure that there is no preliminary polymerization of the composite material. How to use and store composite material and adhesive. After curing a portion of the composite from the syringe, immediately close the syringe with a protective cap to prevent light from entering the syringe. The adhesive is shaken well, dripped into the pellet, and covered with a protective lid. The adhesive bottle is immediately closed to avoid evaporation of the solvent and activation of the polymerization initiator. The material is stored at a temperature of 21 to 24 degrees, but nanocomposites and adhesive of the 6th and the 7th generations are kept in the refrigerator at plus 10 degrees Celsius. Strictly observe the shelf life of the material and adhesive and do not use it if the due date is over. How do we use a composite material? There are either 2 points from which we may choose the composite material. These are the aesthetics and the function. The color categories of the shade of the material: A. Orange-red spectrum, B. Orange-yellow, C. Brown-gray, and D is brown. The minimum saturation of Q is defined by number 1, or if we are talking about the letter D, the brown colors, it's number 2. Average saturation is once again coded with some number in the shades, and in all shades it's number 2. The maximum saturation is number 4 in all shades. Thus, we determine the color by the amount of shade. And for example, if we need orange-red color with maximum saturation, we should choose the color A4. But if we need the brown color with minimum saturation, then we will choose the number D2. The color of incisors and canines is in spectrum of 580 nanometers, the orange-red, which is the group of colors A in most of the patients. On this slide, you can see the variability of shades of different composite materials. On this slide, you can see an optical model of the crown, from up to down. The aprismatic enamel, reticular enamel, enamel dentinal junction, the zone of fluorescence, the main regular or primary dentin, it's also called the mantle dentin, and the secondary dentin, which is forming around the pulp. Different tooth tissues have different opacity. The predentin has 77% opacity and the main masking tone for pulp covering. The mantle dentin has 50% opacity and 85% of people have a red-orange shade of dentin. The base enamel has 41% opacity. Its color is usually yellow, but due to transparency, it doesn't define the tooth color. And surface enamel is colorless and has 12% opacity, which means that it's almost transparent. To restore the frontal teeth, multi-layer restorations are used. With an opaque layer, which is blocking the light, the dentinal layer, which is translucent and has some degree of transparency, and the composite used for it are called the dentin or body composites. The enamel layer is transparent but having color, is usually enamel A2, yellow enamel or white enamel, and surface level enamel is ultra-transparent and colorless. Thank you for your attention.